In this video, we're going to talk about pre-training encoders. Okay, in the last video, we talked about how we can pre-train decoders. And I told you training only the decoders is similar to training single RNN because we can condition on, we cannot condition on future words. And training on the encoder parts is similar to training by RNN because we can have both forward and backward context, and we can condition on future. However, it is not actually future. We are just given the whole sentence at once. However, in this case, we get one input at a time and get one output and use this output as next time steps input and get the next output and use this as the next time steps input. And we repeat this process again and again. And in the case of encoders, we receive the whole sentence at once and get both forward and backward context and perform some transformation of the input sequence into another type, or perform something like sentence classification. Okay, and when we use only encoders, what pre-training objective should you use? So far, we looked at language model pre-training, like giving W1 and make it to predict W2, and input W2 and make it predict W3, like this. However, in the case of encoders, it receives bidirectional context, and we can't do language modeling. Therefore, we need to come up with something different pre-training scheme. And this is the idea that came out in 2018. Because we have the whole sentence, what this paper proposed was masking some parts of the sentence and let this model predict these masked tokens. In this example, I went to the store is the input sentence. However, we masked out the went and store words. And we just pass mask token to this encoder. And this encoder's job is to predict the went and store words. And we are going to only add lost terms from words that are masked out. And this scheme is called masked language model. This is how we are going to train encoders. And this model is called bidirectional encoder representations from transformers, abbreviated as BERT. It came out in 2018, and its weights were also released in 2018. And more specifically, how we make masks. The job of this BERT model is to predict a random 15% of word tokens. Therefore, 75% of the sentence parts are given. However, only 15 of them are masked out. And among those 15 masks, 80 of them are replaced with the masked token. And another 10% of the words that are selected, like so. Given this whole sentence, we select 15% of the words. And among these 15, 80 of them becomes mask token. And 10% of them becomes a random word. Here, I went to the store is the given input. However, this went became pizza. So this 10% of the words became random words. And the rest 10% is unchanged. And the job of this encoder is predict these words, whether this is a random word or this is a correct word. And if this is a mask token, it has to fill out this mask. And by diversifying the masks, the representation power of this encoder improves. And as GPT architecture, this BERT model is a unified architecture. What I mean by unified architecture is that for downstream tasks, you don't have to come up with different architecture than the original architecture. And there is minimal change between the original or pre-training architecture and the downstream architectures. How can you achieve that? But first of all, let's talk about the training process in more detail. For training BERT architecture, we need to use 3 types of embeddings. The first one is called token embedding. And the second one is segment embeddings. And the third one is position embeddings. We already saw what position embeddings were. And what is token embedding? We know this. This is similar to like word vectors. However, there are some special tokens like CLS and separation. Because when we are training BERT, we need to feed 2 sentences or more than 2 sentences. And this separation token separates or distinguish these 2 sentences. Like this sentence ends up here, ends here, and this separation token signifies that another sentence starts here. And this CLS token represents all input. I'm going to talk about the detail of the CLS token in the following slide. And what about this segment embedding? This embedding is to represent the first sentence and second sentence like this. Therefore, these inputs have 2 segments, segment A and segment B. So as you can see here, BERT architecture requires 3 embeddings: token embedding, segment embedding, and position embedding. And then we identify 50%, we select 50% of the words, and 80 of them becomes mask token, and 10% of them becomes random words, and the last 10% is unchanged. And then we pass through, so this becomes input, and after passing the decoder, the encoder, it should output here my name, my dog. So dog should be here. He likes playing. What was the word? Yeah, ing. So this should be the output. And what is the purpose of using CLS token? CLS token is to represent the whole sentence. And after passing through this encoder part, I told you that this one is, let's say this one is mask, and this one is mask, and this part should output shop ing, and this part should output is. And what about this part? This part outputs 1 or 0. 1 for if these 2 sentences are neighbors, otherwise 0. Therefore, this BERT architecture encodes all the information from these inputs into this position. So each position represents the information of the corresponding word, input word, and this position gathers all the information from the sentences, and the information is represented in this position. Okay. This is very helpful for some downstream tasks like image and sentence classification or sentiment analysis like that. And this BERT model was pre-trained on the books corpus dataset plus English Wikipedia. And this model shows very remarkable performance, showing 4 perplexity, and it contains 110 million parameters, 12 layers, and 768 hidden sides, and 12 attention heads. And we just need to change the input and output format for different downstream tasks. We don't have to change the architecture. The only thing we need to do is just change the input and output format. For example, for paraphrase detection, we just input sentence A and sentence B separated by the SEP token. And then we get the output from where the CLS token is and add one small linear classifier. And this will output 1 or 0. 1 for if the 2 sentences are paraphrased ones, then it will output 1, otherwise 0. And for sequence tagging, we just input text and PED. PED for representing handling different sizes of input. And we just add token embeddings and get linear classifiers, add linear classifiers for each position. And then we can get tags. And for text classification, this is about the whole context of the sentence. Therefore, we are going to use just CLS position. So depending on whether we need to use the whole summarized context or just separate positional information, we would use the CLS token or its positions embedding. So that's the difference. That's the only difference. And this BERT model shows very good performance on downstream tasks, especially GLUE benchmark dataset, which is a collection of enabled tasks. It shows state-of-the-art performance at the time, like this. It even outperformed OpenAI's GPT at the time. And at the time, GPT and BERT were competing each other. And nowadays, I don't know, those two are like most popular foundation models in natural language processing. And it also performed very well on SQuAD dataset. What is this SQuAD dataset? This dataset is Stanford question and answering dataset. It consists of a total of 98,178 questions. And it is like solving some English problem. So given a paragraph, based on this paragraph, it has to answer these questions. Like, what causes precipitation to fall? The answer is gravity, and gravity is here. Like, what is another main form of precipitation besides drizzle, rain, snow, sleet, and hail? This. Okay, and the answer types are quite well distributed. And at the time, even it was 2020, these models outperformed human. A human's performance was like this. However, these Albert, other models already outperformed human performance. And let's have a look at a specific example. How can you fine-tune for this SQuAD task? For example, this has a reference, and from this reference, we need to answer this question. How many parameters does BERT large have? By reading this paragraph, BERT large is really big. It has 24 layers and an embedding size of 1024 for a total of 340 million parameters. And by reading this paragraph, you already know that the answer is 340 million parameters. Altogether, it is 1.3 gigabytes, so expect it to take a couple minutes to download to our Colab instance. And to solve this squad task, what we can do is following the CLS token, we add the question sentence and add the separation token and add the reference text like this. And what we do is let this BERT model to predict the start span. The start span means where this answer for this question starts and ends. And as you can see here, this BERT model predicts the starting point is here, like 340. And it predicts the end position for this answer is millimeter or million or these parameters. So both are okay, right? And this is how we tackle the squad task with this BERT architecture. We don't have to change anything. However, we just need to formulate the input and output forms and how, that is basically what we do to use BERT models for this squad task. And as you can see here, to employ this BERT model for your application, you just need to think about how you can formulate your input and output. That's all. Okay. And of course, there are some limitations of training encoders. And one of them is we cannot very well generate sequences because it has to receive the whole sentence at once. Therefore, this pre-trained encoder, BERT, don't naturally lead to nice autoregressiveness. Autoregress is getting one output at a time and use that output as next time steps input, like this. However, we cannot implement this kind of behavior naturally with BERT architecture. And there are also extended versions, enhanced version of BERT. Two are quite famous. The first one is RoBERTa. This just mainly train BERT for longer and remove next sentence prediction. This paper argues that next sentence prediction does not help improve the performance. Therefore, they did not use this task. However, they trained BERT for a longer time. And at the time, researchers figured out that BERT models experience underfitting. What I mean by this underfitting is, when making a prediction, not all parameters contribute to that prediction. However, only part of the parameters contributed to making prediction. Therefore, BERT has to be trained longer. And this paper figured that out and just trained BERT for a longer time. And the second paper is SpanBERT, and it figured out that masking contiguous spans of words makes a harder, more useful pre-training task. So rather than masking out random sentences, parts like this, it masks out contiguous parts like this. And a takeaway from this RoBERTa paper is more compute, more data can improve pre-training, even when not changing the underlying transformer encoder. Here, as you can see here, pre-training longer leads to better performance like this. All right, up to this point, we talked about how we can pre-train encoders. And let's talk about pre-training both encoders and decoders. Okay, this is the architecture. We use both encoder and decoder, basically the whole transformer architecture. Okay, then what pre-training objective should you use to pre-train this transformer architecture? We could do something similar to language modeling. However, this encoder part has to receive the whole sentence. Therefore, we give some context like this from time step 1 to capital T. We give this sentence and let this model predict the words after capital T plus 1. This is basically what we can do to pre-train the whole transformer architecture. And the encoder portion benefits from bidirectional context, and the decoder portion is used to train the whole model through language modeling. And another scheme is called span corruption, and this model is called T5. What is span corruption? Given the original text, we corrupt or erase some part randomly like this. And we give this corrupted input into this encoder. And decoder recovers these corrupted parts like this. Okay. And this is also similar to language modeling. However, the bidirectional context is given in the encoder part, and the decoder uses those bidirectional contexts to recover the corrupted parts. And these encoder decoders work better than only decoder parts. And a fascinating property of T5 is it can be fine-tuned to answer a wide range of questions, retrieving knowledge from its parameters. Okay? And basically, these three architectures, like encoder parts, decoder parts, or encoder-decoder parts, all work quite well for downstream tasks. Okay. Up to this point, we talked about training decoders and training encoders and training the whole architecture, encoder plus decoder. Nowadays, people generally use decoder or encoder only parameters or architectures. And depending on your application, if your application needs to receive the whole sentence at a time, then you can use encoder-based architectures. And if your application is focusing on generating new sentences, like chatbot or dialogue generation, then you might use GPT-based architectures or decoder-based architectures. Therefore, depending on your application, you need to choose your own architecture. All right? Okay, from next video, we're going to implement some of these architectures and have a look at some technical parts.